Hello, everyone. This is Carlos Lara from the Research Center in Mathematics at Zacatecas, Mexico. The Research Center in Mathematics is opening a new master degree program in robotics. To celebrate this event, we organized a series of talks on robotics and human-computer interaction. Our invited speaker today is the Professor Stephen Brewster. Thanks for accepting our invitation, Professor Brewster. And let me introduce him. Currently, he is Professor of Human-Computer Interaction in the School of Computing Science at the University of Glasgow. His main research interest is in multimodal human-computer interaction, sound, haptics, and gestures. He has done a lot of the research in earguns, a particular form of non-speech sounds. Professor Brewster got a degree in computer science at the University of Hertfordshire in the United Kingdom. After a period of industry, he did his PhD in Human-Computer Interaction Group at the University of York in the UK. The title of his thesis was providing a structured method for integrating non-speech audio into human-computer interfaces. That is where he developed the interest in earguns and non-speech sound. After finishing his PhD, he worked as research fellow for the European Union as part of the European Research Consortium for Informatics and Mathematics. He is member of the KISS research section, and within that, he leads the multimodal interaction group, doing world-leading research in human-computer interaction. He is a fellow of the Royal Society of Edinburgh and a member of the ACM SIGCHI Academy and ACM Distinguished Speaker. Please welcome Professor Brewster.
Thank you. Right, let me share my slides. Can you see my slides okay?
Yes, perfectly.
Good. Thank you, Carlos, for the invitation. Very happy to meet you all. The last time I saw Carlos was in Colombia when we were both visiting there. And I was trying to learn how to do dancing and trying to copy Carlos, who was much better at it than I was. Anyway, let's move on to the topic of the day, which is all about ultrasound. So we have a project going on looking at how we can use ultrasound for human-computer interaction. And ultrasound could do some interesting things which other technologies can't. So I'm going to try and talk about some of those and see if, so I'll show you some videos, see if I can convince you that ultrasound is an interaction technique of the future. So where am I from? So I'm right over there on the right-hand side. I hope I've got the university your university in the right place there. So kind of a long way away. It's a shame that I can't come to visit you face to face. Maybe after the COVID crisis is over. This is what the university looks like. So some people think if you're a fan of Harry Potter, that it looks like Hogwarts, the school where Harry Potter goes to school. So we have a kind of nice old building. Unfortunately, my office isn't in the nice old part, but there we are. Looks nice in the photographs. So I'm part of the Glasgow Interactive Systems section, which is in the computer science department at the university. So we are interested in all sorts of different aspects of human-computer interaction, or HCI. As Carlos mentioned, my main interest is in multimodal human-computer interaction. I'll tell you what that is in a minute. We have others in our group who work on social robotics, social signal processing. We have people who work on ethics and trust in data. We have usable security. We have a new faculty member who works on animal-computer interaction. So we're pretty broad in the range of things that we do. And you can see our webpage there. So for those of you coming from different backgrounds, what is human-computer interaction? Well, the ACM, which is the kind of professional organization of computing, they define it as a discipline concerned with the design, evaluation, and implementation of interactive computing systems for human use and with the study of major phenomena surrounding them. So it's really all about humans using technology, trying to make the technology easier to use, make it accessible to more different types of users doing different types of things in different situations. So the particular part that I'm most interested in is this idea of the multimodal interaction. This is how we can let the users use all the capabilities that they have to interact with the technology. If you think about it now, most of the time I'm just using my eyes to look at the screen and I'm using my fingers to type on a keyboard or touch screen. I'm not really using all the things that I've got as a human. Now, I've got a rich sense of touch, I've got a sense of smell, I've got a good sense of hearing, taste, and I've got all these different capabilities. And I can do input by speech, I can do input by gestures, all sorts of things. But quite a lot of the time, our technology doesn't take advantage of those. So the aim of multimodal interaction is to really see how we can use those. So it's to investigate human capabilities, what is it that humans can do, and then design interaction techniques and applications that can take advantage of these. So for example, it might be that if you have a visual impairment, you can't use the screen, you need another way to get your information. So perhaps you could use sound. Or if you have a motor impairment, maybe using a keyboard is difficult. How can you do input in a different situation? So we're kind of thinking about all range of different types of users, all types of applications. So one of the areas that we've mostly been focusing on, I'll talk more about today, is this area of haptics. So that's anything to do with your sense of touch. So how can you use touch for input? It might be gestures, it might be force, by applying force. It might be the vibration that you get from your mobile phone when you receive a message, all sorts of different things. Your sense of touch is very rich, but really our devices don't take advantage of that. So mostly what I'm going to talk about today is how we can use ultrasound, but there are all sorts of other aspects of haptics that we and lots of other people are also researching. The other things we do, well, we look at this in terms of VR and AR quite a lot. So how do we do good interaction in virtual reality or augmented reality? So we're very interested in multimodal interaction in augmented and virtual reality. Lots of work on touchscreens, and now touchscreens, of course, are moving from phones to everywhere. So we move a lot of our work over to in-car user interfaces. Many new cars now have touchscreens, and how can you operate those in the car? Is it safer than using the physical controls they used to be in the old days? We do things with interaction with TV. We look with accessibility, as I mentioned before. A lot of work on multimodal interaction is to help people with impairments, visual impairments or physical impairments. And we also have a strand of work on mental health as well, looking at how we might use technology to support mental health. We have projects on dementia and brain injury and things like that. But what we're going to talk about today, ultrasound interaction. So this might not be something that you've really thought very much about before, but as I said at the beginning, ultrasound has got some interesting capabilities for humans. So if you think back to your school physics, if you combine two sound waves, it's in the bottom of the slide there, you get these interference patterns. So sometimes the wavefronts come together and they create a stronger force, and sometimes they interfere and create a weaker force. So you get this area of high pressure. So you can see, for example, in the middle between source 1 and source 2 there, you get a high pressure region. So what that means is that we can create feelable forces in the air. So I could put my hand in the air and then I can have a force beamed to it, so I can feel something in midair. That's quite interesting because it's a non-contact form of haptics. Normally, if you think about haptics, you have to be in touch with your phone in order to get the vibration feedback. If you're not touching it, you can't feel it. You might be able to hear the phone vibrating on the table, but you can't touch it. You've got to touch it. So the interesting thing about ultrasound is you can put your hand in space, and then we can beam ultrasound forces to it. wherever we want to. So it's a non-contact form of haptics. How do we do it? Well, the hardware isn't very complicated. So actually, the hardware that we use is the same as would be in a car, which would stop you reversing into a wall. So these are the ultrasound transducers that would be in the bumper of a car, which would then fire out ultrasound, is picked up by a detector, and then can tell you whether you're about to bump into something when you're reversing. So the loudspeakers themselves, they're just fancy loudspeakers, nothing particularly unusual. It's the way we combine them that's most interesting. By combining the timings and the amplitudes very carefully across this big array, then we can create strong forces. Now, in a presentation, it's a bit hard to show the forces because it's invisible. So here's a little video. You can see the array of loudspeakers at the bottom, and you can see these pieces of paper moving as we control the force generated above that array in different places across the array. So it's a little bit hard to show it because it's invisible, but you can see it through these pieces of paper moving. Here's another way to show it. So this is called Schlieren imaging. So this is a way of seeing a sound field. So you can see the sound waves moving from the left-hand side to the right-hand side. You can see now we put this obstacle in the sound field. You can see the sound waves bouncing off it. So where that hits the obstacle, the forces would be felt. So you can put your hand into there, and then you can feel that force against your hand. So you're not touching anything, the sound is just being beamed towards your hand, and then you can feel that as a force. Now, ultrasound, of course, it's very high frequency. Those loudspeakers we use are about 40 to 44 kilohertz. Now, your skin, you can't feel anything of that high frequency on your skin. So what we do is we modulate that down to about 250 hertz. So 250 wavefronts against your hand per second. And that is a frequency that you can feel. That's not far off the kind of frequency you might get from your mobile phone's vibration motor. So through that, then we can produce texture, we can produce roughness, we can position the feedback at different points on your hand. And the traditional way of doing that is by amplitude modulation. So you just control the amplitude, turning it on and turning it off again. And that works well, but reduces the overall amount of force because sometimes the loudspeakers are turned off. And the force is not that strong because you're just moving air. So you want to have as much force as possible. So we developed a new technique called spatiotemporal modulation. In this case, we can run the sound at maximum amplitude all the time, but we then move it around quickly around a focal point. And that still creates the feeling of a single point of contact against your hand, but gives you much larger force. And also then we can move it more quickly around your whole hand and create a larger area of haptic force if we want to. So for example, if you wanted to represent a circle on the hand, we could do that, draw that circle 100 times per second. You get the feeling of a solid circle on your hand, but with a higher intensity or higher force. And this rendering has a big impact on perception. Because you're just pushing air against a person's hand, then if you're not careful, it doesn't feel very strong. But if you do it right, you can create a strong feeling. So some of the earliest work in this field was looking at, again, this was using amplitude modulation. So the simple technique was looking at how you can perceive force on the hand, where you can perceive it, how far the points would have to be apart before you can detect them, looking at motion and things like that. And as it turns out, yes, humans are very sensitive, so we can create zones of haptic force with about 8.5 millimeters gap between them to be detectable. Actually, the y-axis is a bit worse than the x-axis, and it's better near the center of the hand, near the center of the palm, than the edges. Part of that is just because the way the mechanoreceptors are laid out in your skin, the sensors that are inside your skin. That's nothing really to do with the ultrasound. And we can control motion very well. So we can, by moving a point around on your hand, we can create a feeling of motion, or if we move it fast enough, then we can create a solid feeling. And so with this hardware, we got good control over the position of these focal points of sound, and where we put them and how we move them. So what can we do with them once we can control them? So one of the applications we were looking at was this idea of virtual controls. So maybe you can create some controls in midair when you need them. Here's an example one maybe. So maybe this device is by the side of your PC and you want to have a slider. You could pop up the slider in space next to your computer. You can feel it with your sense of touch. You can slide the slider. When you don't need it anymore, the slider disappears. So you can create these controls when you need them. We also looked at this in car dashboards. So instead of having to reach out to touch a control, you can put your hand out, and then we can draw the control underneath your hand so that you don't have to reach across and try and find the controls and get distracted from the road. You can feel them. And we've also looked at using them with phones. I'll give you some examples of that in a minute, but that you can create controls above your phone. So it may be that then you can interact above your phone and then feel the controls above your device. So your phone is always going to have a small screen, but you can then create a larger interaction space by projecting the haptics above the phone. So yeah, you can create different types of controls. You can create sliders, dials, buttons, all sorts of different things. So one of the particular examples that we worked on was looking at how you might use ultrasound haptics for above and around a phone. Now, for a little while, phones have used the cameras on the front to be able to detect your fingers to enable interaction. But the trouble with that is, for these mid-air gestures, there's no feedback. There's nothing to touch. And that often leads to poor interaction and poor usability because there's nothing to touch. You can maybe see something on the screen, but maybe your hand is obscuring the screen so you can't see it anymore. So the nice thing you could do with ultrasound haptics is project the haptics onto your hand so you can feel it, but still interact above the phone. So you can do gestures, but you get the haptic feedback. And that's been shown in the past to give you much better interaction, high quality interaction. That brings up some interesting problems though, particularly is that you might have sound fields with got holes in them. So if you think about how you might use some kind of ultrasound device with your phone, you could have it in different types of orientations. So maybe the one on the left, you have your phone and then the ultrasound loudspeakers are around the edge. But that means there's no speakers in the middle. Therefore, there's a gap. Or maybe you have them coming out the sides or the bottom or the top. So there may be a gap in the ultrasound speakers, which creates holes in the sound field. So on this particular project that we did with Huawei, we were looking at how you might be able to use arrays of speakers with holes in them. So here's one example. This one doesn't have a hole in it. This is just basically the idea of an accessory that might slide out from the back of your phone and then give you an array of transducers at the side. But the nice thing about this one is what it does when you're above the phone. So what you can see then on the top left is your phone and your array of speakers. And then the graphs, the heat maps, show you the amount of force at various different heights above the array. Very close to the surface of the array in the first one, you can see there's a slight purple on the left and then it's black on the right. Your hand is very close to the array. And if it's too close, then the sound beams where we're beaming at your hand can't really form, so you don't get much force. But as you see, you move your hand up a bit higher, then you start to get a stronger feeling of force. And actually, if you get to say about 10 centimeters, 20 centimeters, the sound then starts to spread over the surface of the phone. So not only do you get a sound haptic field over the array, you also get sound over the phone as well. So that means that I can do interactions over my phone and still get haptic feedback. And of course, as you get higher up, further away from the array, the forces get a bit weaker. But when you're when you're in 10 to 15, 20 centimeters above the phone, you get quite strong force, and then you can interact over the phone or the array. So it gives you a nice interaction space. So it does show that you can create useful sound fields from arrays with holes in them, which you could then use as accessories on phones. So yeah, we can create forces in the air for non-contact haptics. So the really interesting thing is here, you don't have to be physically touching anything. We can beam that to you. It's very well perceived by users. People like it, but the forces are not that strong unless you take care about the rendering. And yeah, we can create interesting transducer layouts. Interesting, maybe it's got holes in it, it's asymmetrical, and with some clever modeling of the sound, of the shape of the array, you can still create good quality haptic feedback. We've still been thinking about how you may also do stronger forces, because the forces are, it's only air that's being moved, so it's not super strong. We just had a paper published last month looking at how you might do pseudo haptics, which is using some kind of visual tricks to kind of help the haptics feel stronger. We've also used some audio alongside the haptics. Again, that can make it feel rougher or smoother. So you can manipulate people's perception by using this multimodal feedback, by using feedback in multiple senses at the same time. So it's a nice example also there of multimodal interaction. So that's the first part. We can use ultrasound for generating haptic feedback, but we can also do other things with it which are potentially more interesting. So levitation. So this is a project which we're running right now, and this has this kind of grand aim of creating a radical new human-computer interaction paradigm that empowers the unadorned user to reach into a new kind of display composed of levitating matter. That sounds kind of very grand and amazing, but what we're trying to do in this case is get away from the virtual pixels that we're all using on the screens in front of us and create physical pixels made out of physical things that we can then use as displays. So this uses the same hardware as I used before. If you think about the forces that I was beaming to your hand, well, we can also use those forces to hold objects in the air. So we use phased array ultrasound. So that's controlling the timing very precisely across the loudspeakers in that array. So we can do that. We can support objects in the air. Now, these are small objects. What we're talking about as small styrofoam beads, about maybe 2 millimeters up to 4 millimeters in size. So these act like physical pixels. So not the pixels on your screen, but these are physical pixels that we can control. So the idea is that then, because these are very small, we can then compose them into complex displays and build physical models. We can build 3D models. So by creating a set of 100 of these pixels in space, we can create a model of something. So people often say, is this the kind of levitation which could levitate a person or some kind of object? That's not the aim here. There's other ones you can use for that. Electromagnetic levitation has been around a long time. The thing about electromagnetic levitation is good for very large things, but it's not good for very small and very precisely controlled things. The thing about ultrasound is it's very precise, so we can do very precisely controlled things. I'll give you some examples of types of things we can do. Here's an example to show you that we're not cheating. So here's a simple array. You can see that this time there's 2 arrays of those loudspeakers, top and bottom, and those white dots are the small polystyrene beads. So they're held up inside the soundscape, in this case using standing waves between those 2 arrays of speakers, and you can see that we can move them around. This is an early prototype. It kind of gives you the idea. And you can see there's no string holding them up. We're not cheating. There's no magic. We're holding those beads in place. So that was one of our early prototypes. Here's a more recent one where we've been looking at more kind of complex motions. So here you can see and we've got 4 beads being levitated. This is a much larger levitation device, but again, you can see the array at the bottom. There's also another array at the top. So here we can control the corners of these 4 beads to make the corners of a cube, and then control their motion. In this case, a rotation. Next slide. Here's another rotation, this time in a different dimension. So this is actually much harder to do than the other dimension, because here you're rotating in and out of these standing waves. So getting the beads to line up and then move out of the standing wave is difficult. You can see them shaking around a little bit more because it's more unstable. A lot of the work here really comes down to clever acoustics, and we work, as part of this project, we work with some great acousticians in Sweden who help us with designing these sound fields. And we were very happy when we managed to get it to rotate in and out of the vertical, because moving in and out of the same standing wave is very difficult. But what these things show is that we've got good control of these individual pixels. We can move them around and control what we do with them in space. Now, of course, we're not just interested in this as a display. We're also interested in it as a form of interaction. So here's Ewan, one of the guys working with me on the project. So looking at how we might do interaction. So you can see in front there, if you can see that, there's a leap motion controller detecting his hands. And then you can see he's able to do different kind of interactions. So we can map the controls, the motions from the gesture sensor to the beads in the array, so we can actually interact with it. The other interesting thing you can do is integrate other objects into the display. So here we've got some objects made of this felt material and this wire mesh. So the interesting thing about these materials is that they're acoustically transparent, so the sound passes through them. So they have no effect on the sound field. So you can see here we're kind of simulating the game where you have to play it again, where you have to run the metal hoop along the wire. If you touch the wire, you know, the sound, the buzzer sounds, and you lose the game. So here we can move the bead through these tubes, and you can still keep it in control, still move the bead. There's just a couple of other examples. So here we were looking at moving the bead above other kinds of static surfaces. So here, this might be some kind of map showing the heights of mountains or contours or something like that. So we can do the levitation through this material. Now, this might be you plotting your route, climbing a mountain or something like that. So we can do the levitation. We can also, of course, do haptics through here as well, because it's the same sound. So you can feel haptic forces or the beads. I think actually this one shows the haptics as well. So again, you can see the pieces of paper moving when we project haptic forces through those objects. So the interesting thing here is that you can then create displays, physical displays with physical materials, and then project haptics or do levitation above and around them. So some applications, yeah, we've been thinking about dynamic 3D physical displays. So maybe you're a 3D model designer, so you can create an object in front of you in 3D with these physical pixels. You can change it and interact with it, change its shape if you want to, and then it can go away again if you don't want it. Now, you might do this now with a 3D modeling package or even with a VR headset. But with the VR headset, you're having to trick your eyes into seeing the 3D. It's not real 3D, but with enough pixels, we can create a real 3D object in front of you. It then may look really like your coffee cup, in which case you can interact with it. You can share that with other people because it's just sitting in front of you. So it's easy to share. We've looked at presenting data, so you can present dynamic data You can have that object, that model change in shape over time. So it gives you new ways to understand your data and your information. And it's very easy to share. It's using all your natural human capabilities. Now I can interact with it using my sense of touch. I can look at it. It's not a trick in any way to make my eyes think it's 3D. You know, it's really 3D. And also, it's very fast. It might be that you might print a 3D object or something like that to see if you've designed it correctly. But that takes some time and costs some money. But it might be that in our case, you just generate a 3D model in physical pixels and say, no, that's not quite right. I need to change this bit here, stretch this bit here. Then you get it right, and then you can send it away for 3D printing if you're happy with it. So the whole process becomes much more interactive and much faster. So talking about interaction, a big thing that we've focused on is how do we interact with these levitating pixels? It's one thing to levitate them, and actually the levitation is not so difficult. Static levitation is not so difficult. But when you need to interact with them, move them around and control them, then things start to become a little bit more difficult. So one issue is that you can't touch those physical pixels in the array there. If you touch them, they're just polystyrene. They're only held up by air, so it's very easy to knock them out. So what we try and do is interact just in front of them, as you saw in the previous picture. The gesture sensor is just in front of the array. So you can interact in front of the array, then your interactions are reflected in the array. So the first thing we did was looking at selection. Selection, pretty fundamental. You've got to be able to choose an object in the display for any interaction to take place. But the interesting thing about these kind of arrays is that there's only the objects there. There's nothing else. How do you indicate which object that you've selected? So what we've done is we've changed the object itself and make it shake around to indicate that it's selected. Now, potentially you could, of course, project on them or something like that. But in the simplest case anyway, all you've got is a pixel. So you've got to do something with the pixels. So I'll show a little video of how it works. So you can see we're pointing at an object and we make it vibrate slightly. And that's the way that we can indicate that which one you've chosen in this array of multiple pixels. So we just project a ray from your finger towards the objects, and then you can choose which one. And the one you hit starts vibrating. Pretty straightforward, works really well. One issue, of course, is the ability of humans to point very precisely. So our beads are about 2 millimeters up to 4 millimeters in size. And actually, it's pretty hard to point at something 2 millimeters in size within an array of pixels. So actually what we did was we looked at putting a kind of zone around each pixel in order to make it bigger, make it easier to point at. So you can see from the graph here that with a very small target, we started up with a 5 millimeter zone, so plus or minus 2 millimeters. It's pretty hard. It takes you a long time. That was taking 7 seconds to choose an item, which is pretty slow. And of course, as you make the size of the target bigger, not surprisingly, it gets much easier to select it. But of course, as the zone around each target gets bigger, that makes the display less dense or lowers your resolution because you can't have the pixels so close together. So you can see from the graph the kind of trade-off that you get there by increasing the size. So generally, we've been sticking at maybe 15 to 20 millimeters, plus or minus 20 millimeters around the center to give a reasonable interaction speed, but not make the display too low resolution. Now, the next problem that occurs, of course, is this is a 3D display. So how do you select items that are not the front one? So in a simple experiment, we just turn the array 90 degrees from what we had it in the one I showed you before. And now we started to think about occlusion. So how do I detect the one that's not the front one? So we came up with a technique called lock ray. So what you do here You point at a set of objects, and that ray comes out of your finger, and you select the set of objects which are on that line. Then you put out your thumb, and as you move your finger backwards and forwards, then you're kind of moving a cursor along that array of objects. And the one that you stop at, that then starts shaking around. You'll see it better in the video. So you see them both shaking. I've selected all the items on that row. And then stick out your thumb. And then you move backwards and forwards to select the individual items on that row. So now that would allow you to select any number of items stacked up in depth. So we did a user study to look at that. And set the target to be about 20 millimeters plus or minus 10, so 20 millimeters in size, to make it a little bit easier for them to point at. So selection time, about 2.5 seconds for those items in the array, and about 95% accuracy. So people were pretty good at making those kind of selections. Of course, the selection time would increase depending on how many items you had in that in that dimension, but it works pretty well. So you can select these obstacles further back. Now, another interesting problem that comes up with such physical displays as this is obstacle avoidance. So with virtual pixels, this is not a problem. I can move pixels around and they can overlap each other, and there's no problem because they're not physical things. But of course, if I have two pixels, they're going to bump into each other if I move one into each other. So I need to think about how to deal with this issue. If I want to move this pixel past this pixel, I've got to do something to get it out of the way. This is particularly important for dragging, if you want to drag objects around in your display. And this occurs in any display with physical things in it. So this would be the same if you had an array of drones flying in the air and you want to move the drones around. Is a kind of fundamental problem for any interaction technique or any display where you have physical things. So there's lots of different things you can do. So you can shift things out of the way, you can divert them, you can repel them, swap them. I'll show you some examples of these in a video in a minute. And you can either move the particle that the user's controlling, or you can move the obstacle. So we conducted a big study to try and find out what the best way of doing this was. Yeah, as a spoiler, actually the divert obstacle one was the best, but let me show you a video of some of this so you can see what's going on.
Levitating particle displays show content composed of several physical particles levitating in air. It's necessary to enforce constraints between physical particles to avoid them colliding. If two particles get too close together, for example, they might get stuck in the same trap, becoming inseparable. We developed 10 interaction techniques for avoiding collisions during particle movement. These manipulate the position of the obstacle or the controlled particle to keep them apart. Shift obstacle instantly translates the obstacle particle so the user particle can continue along its trajectory. Shift user instantly translates the user particle so that it avoids the obstacle. Shift both combines these techniques.
Now, I'm not going to show you all of those, but that was in a simulation. What I'll show you is just a couple of them actually in practice in our array. It all looks easy in the video, but actually when you try to do this, in a real sound field with real particles, it's actually quite difficult. So here's the repel obstacle.
Repel obstacle uses a repulsive force from the user-controlled particle, forcing the obstacle out of the way.
You can see it moving in the background there.
Repel user uses a repulsive force from the obstacle particle, forcing the user particle to travel around it. Repel both combines these. Divert obstacle incrementally offsets the obstacle particle so the user particle can continue along its trajectory. Divert user moves the user particle on a curved path around the obstacle. Divert both combines these.
You get the idea. Hopefully you could hear Ewan's nice Scottish accent as well. So I think that brings up some some really interesting problems that you just don't get those kind of issues in virtual pixel displays, the kind of things that we're used to on desktops and computer screens. Now, there's these physical constraints you suddenly have to start thinking about. They don't happen when you pixels. The pixels don't really exist; they're just virtual things. But when the pixels are physically there, you have to do something about it. Now, of course, one problem comes when you're trying to move these things, is that, of course, if I move one pixel out of the way, so I'm dragging along, I move this pixel out of the way, well, what happens if there's another pixel here? Then this one has to move. And maybe then you may get these kind of cascading effects of moving the pixels. So that's something that we're looking at the moment, because eventually, you'd end up pushing things out the side of the array because you had to move so many things. So the scaling is really an issue here. What we want to do is create arrays of thousands or millions of pixels eventually, so we can create really high resolution objects. And that's fine if the objects don't need to move or be manipulated. But as soon as you want to start controlling and manipulating them, then you have to deal with these physical constraints. So what do you do with those pixels when you move them if there are others in the way? So we have got plans for that, and we've done some pilot testing of different things around those, of trying to reduce the amount you need to move each time, especially if you have this zone around each pixel, which I mentioned before, enables you to point at it more accurately. Well, that gives you some free space that you can use to push the pixels closer together, because you're not interacting with those, you're only interacting with the one in the front. So there are things you can do. But there's really interesting scaling problems here that are different to the kind of scaling problems that you have by just buying a bigger monitor or something like that to put on your PC. Right, let's think about a few conclusions from all these things that I've talked about. So we started off talking about this idea of multimodal human-computer interaction. So here we're looking at, can we create richer interactions between the user and the technology than we have now? Right now, we just use a bit of our eyes and a bit of our fingers, and that's about it most of the time. How can we use all those things that humans are capable of? Humans have got a great sense of hearing. How can we use that? Humans have got a great sense of touch, more than just hitting a screen. We can do all sorts of things with our sense of touch. It's really rich. How do we use that? How do we use our other senses? I've talked about only haptics really, but we've done lots of work on things like smell. We've done work with things about hearing. So there's all sorts of work going on in these other senses. So we started off talking about ultrasound for non-contact haptics. So ultrasound is, it's a highly novel modality. Very little work really going on yet about how it can be used. But the underlying technology is pretty straightforward. We're just using the same loudspeakers that are now in millions or maybe hundreds of millions of cars to stop them reversing into things. So the hardware is nothing very, very difficult. So the hardware is available. It's just using it in an interesting way. So you can combine the sound, the sounds from those loudspeakers. So then to create haptic forces. So I can then make non-contact haptics. I can beam those haptic forces against my hand. And that means I can do haptics wherever. I could have a ring of them around my webcam. I can be doing gestures in front of my webcam. I can be feeling haptic forces from interacting. I can have them coming from my phone. I can have them coming from controls, virtual controls by the side of my PC if I want them. Like I said before, we've also used them in cars. The idea being, if I'm holding the wheel, I can reach out and I can have the control put to where my hand is, rather than me having to reach far to do the controls. I can have it come to my hand. So it can provide rich interaction, maybe improve safety, and I can have the controls appear and disappear when I need them. I don't have to have them there all the time. And then I can have whatever control I want. If I want a slider, I have a slider. If I want a button, I have a button. I can have whatever I need at the time I need it. So it's very flexible and rich and allows you to use that sense of touch. Then the next stage is levitation. So there's something really interesting here, I think, about a totally new form of display. So here we're levitating, controlling these very small physical pixels and controlling them and doing interesting movement and positioning of them. So you can create physical displays. Now at the moment, you know, we can create displays with 10s or 20s of pixels in. There's no reason why you can't scale that up to thousands. It's easy to do that right now if you don't want movement. You wanted a static object. But as soon as you want movement and interaction, then it becomes more difficult. So I like to think about this is, you know, if you think back to the 1960s, pixels were invented. And in a lab somewhere, somebody said, wow, I've created a pixel on the screen. I can make one pixel appear on this screen. Don't know what it's going to be for yet, but it's important. And then, you know, 30, 40 years later, 50 years later, now we've got so many pixels, we don't even count them. So we're at that kind of stage with these physical displays. So we can control the pixels in small numbers. We can make them do what we want. We can position them, but we haven't yet scaled them up to be thousands or millions. But that's really a kind of step on from where we are now. That's what happened from the 60s, 70s, 80s onwards until LCD screens or whatever became completely standard things. You know, we're in that kind of starting point, the birth of these physical pixels. So what we did in our project really, I think, was build the foundations for interaction. So we can create the haptic effects, we can create the levitation effects, we can move the beads around, we can put them where we want them, we can move them quickly, we can position them carefully. And now it's kind of like we can hand this over to the rest of the world and say, okay, right, well, look, we've given you the tools, now go away and create some really crazy applications with them. What things can you do with these that will kind of blow people's minds? Just in the same way that now you can do amazing things with graphical displays. So we've kind of given those initial tools. So now it's kind of open to you guys and everybody else to say, right, okay, I've got a great idea. I want to make something in 3D with these pixels. So we've kind of given you the tools to enable you to do that. So with that, I will finish. Hopefully that's been interesting, and I've told you something about ultrasound and what it can do for haptics and for levitation. I'll stop sharing my screen.
Thank you, Steve. We have enough time for a couple of questions. Do you have some questions?
I have one if nobody else does. No, Hugo.
You first, please. Uziel.
Okay, just about this last part about scaling up, and I'm sorry if you did say it and I missed it. In pixels, I guess the limitation was the number of transistors that we could put in a computer, among other things. But in this case, with what is it? What would need to happen, you think, for it to be able to just blow up?
Yeah, I mean, in the end, it comes down to quite a lot down to the number of loudspeakers. The more loudspeakers, the more force that you create. The other thing is, so I claimed that having these loudspeakers that were used in cars is a good thing, which it is, but it's also a bad thing, because those loudspeakers, they're maybe just under 1 centimeter diameter, and they always run at 40-ish kilohertz. What we would like to do would have actuators that are smaller, so we can make a denser array, so packing more transistors in, or having more pixels, having more loudspeakers, and also increasing the frequency would allow us to create even more precise control. But nobody really manufactures those yet. You don't need those for cars, so the car guys aren't interested in those. So at the moment, there's no commercial use for those small high frequency transducers. Either we've got to persuade a company that they should make them, or some other use case comes along and says, oh, we really need high frequency small transducers. So it's not a dissimilar limitation to the transistor problem, but it's a loudspeaker problem. Really.
Thanks. Hugo?
This is a nice talk, Steve. I like it a lot. This is a new paradigm for human-computer interface, I think so. This array of speakers can bring up a new way to capture the human perception. How do you think about what do you think about neurological disorders applications? Because I think this technology uses the force of the speakers to interact, but interaction can express many ways to interact with different kinds of persons. But how you think about neurological disorders?
Yeah, that's a great idea. So that's not something that we've done much work on, but actually I think it's an interesting area. So, for example, if you had problems grasping, so
Yes.
maybe holding a control might be difficult, or movement, so getting your hand into a particular place to hold a control. Well, we could display that control to your hand wherever it is, so you wouldn't need to reach very far or grasp anything. We can display the haptics to your hand wherever your hand is in the space. So I think it could be quite interesting in your scenario there. That's not one we've done any work on, but I think it's a really good one.
What about the energy consumption? Because this is a array of speakers.
Yeah, I mean it's not huge. So each of those speakers is it's a small loudspeaker. They're designed to be used in cars. So they're not really high power consumption. Of course, you need a lot of them. So our newer arrays have 1024, 512 and 512. Although for the haptic side, you only need a single side. So the power consumption is not terrible. More power is used when you start to move things around. But if things are static in the array, then the power consumption is not so high.
Okay, thank you. This probably would be a interesting solution or new human interaction interface for social robots. Probably we'll contact you.
yeah, I think so. We haven't done anything in that area, but we have some social robots guys in our group, and I think as a way for the robot to communicate with you.
Yes,
is a nice way. You can feel something about the robot even before you've touched it. You can feel its state. One thing that one of the other guys on the project was looking at was a kind of COVID-safe interaction, because
yes,
I can beam an interaction to my hand. I don't have to touch anything anymore. Interaction can come to my hand, so then I don't have to be contaminated by touching something or me touch something else and give something to another person. So again, with the robot, with the social robot, I wouldn't necessarily need to touch it. I could communicate with it through touch, but not physically touching in case there was any contamination. So I think it's interesting in that area.
Thank you. Thanks a lot.
I think Diego have another question.
Yes, thanks, Carlos.
One?
Yes, hello, Steve. Thank you very much for the talk. It was very interesting and exciting. My question is, yes, I was thinking about scalability, as you mentioned. And what about the initialization in scalability? Is like you have to place the pixels one by one, or you can just throw a lot of pixels there and they will settle somehow? And a second question will be, how much time do you think this technology will require to reach like real applications, like maybe in the industry or something?
Yeah, okay. So first one is kind of initialization. So initialization is definitely an interesting problem. You've found a kind of weakness in some way there. So right now, much of our initialization is this.
Yeah.
Next one. Put it in. I don't want to do that a million times. That's not much fun. You can do it. So one of the partners on the project, we had basically a tray of pixels, of those styrofoam pixels, and then use the ultrasound to pick them out and maneuver them into place. So you can do that, but even doing that is pretty slow. Doing that for 1 million is still pretty slow. So there are things you could imagine just getting a whole handful and just throwing them into the array, and then catching them in the zones where you want them to be. So I think there's definitely
maybe some sort of vibration or oscillation for them to take place. Sounds like interesting, no?
Yeah. So I think that's one of the tools that we haven't got a good solution for yet. We've got some simple solutions, but the solution we have doesn't scale up to 1 million. That's definitely something that needs to be worked on a bit more. At the moment, the solutions are a bit kind of handmade. You can't place them in one by one for a large array. That works well for experiments and in small trials, but not for real life. In answer to your second question, so as part of the project, we have a company called Ultraleap. So they right now make ultrasound haptics boards that you can buy. So there are not too many applications yet. There were companies spun off from a university in the UK as part of a previous project we had, but that you can buy one of those boards right now. So the ultrasound haptics part, that's a standard commercial thing. You could buy that right now if you wanted to. They are also thinking about commercializing the levitation part as part of the project that we're now doing, but that's still in process. So I think that's still a little bit further away. And I don't know how long it took. It's an interesting question. How long did it take from the guy who first made a pixel in the engineering lab and say, look, I've made a pixel on my screen, till you could buy a screen with pixels? I don't know how long that time period was. Maybe 10 years, maybe 15 years. It's kind of hard to say, but I imagine it's something similar, that we can do it now and it works in specialized cases, but to buy an off-the-shelf device, well, but again, you see, the devices are off the shelf. You can buy the hardware that we use, those two arrays, you can buy them right now. It's the same array that you use for the haptics. So you could go and buy them right now. It's just the software and the control and the management of the pixels. So in some ways, it's kind of a software-ish problem rather than a hardware problem. So, 10 years maybe, something like that.
Okay. Thank you very much.
Okay, thank you, Steve, for your exciting and interesting talk. We expect that some of these days you can come to Zacatecas, Mexico, and maybe collaborate with our team. Your research line is really interesting. I know that many other of the participants here have some questions. Can you please give us the opportunity to interact with you, maybe with an email or something like that?
Yeah, sure thing. Yeah, please feel free to send me an email, or we can have another Zoom chat in a smaller group if that is more preferable. So yeah, very happy to chat. If there's any research collaborations we can think of doing, between social robots or anything like that, then we're definitely interested. And yes, I would absolutely love to come and visit sometime. of course, and also we're very welcome to come visit us in Glasgow too.
Thank you, Steve. I hope that maybe we are not as well dancers like the Colombians guys, but maybe we can dance another kind of music and you can enjoy it also as well. Thank you so much, Steve. Thank you for your help, and I hope that some of these days we can do some research together. Thank you.
Fantastic. Great. Thank you all. Nice to virtually talk to you all.
Thank you.
Thanks very much.
Let me. I have some. I am going to give a couple of ads. Let me switch to Spanish. La siguiente charla que nosotros tenemos es el día el día viernes 4 de junio, donde nuestros colegas Héctor, Becerra y el doctor Rafael Murrieta de CIMAT van a platicarnos sobre la investigación que hacemos acá en México, en Zacatecas, sobre robótica e interacción humano-robot. Entonces están cordialmente invitados. Y bueno, agradecerles su asistencia, recordarles que nosotros hemos abierto esta maestría en robótica desde reciente creación. Y bueno, actualmente tenemos la convocatoria abierta donde todos ustedes pueden participar. Esos son el par de mensajes. Les agradezco mucho su asistencia.